Welcome everybody to our CFA colloquium. We have a great speaker today. It's a real pleasure for me to introduce to you Dr. Clara Sousa Silva. And Clara is at CFA, as you heard, although she hasn't used her office there yet because it's been only since last September 2020. She's a 51 PEG B fellow, one of those new prize fellowships, and she's taking it at CFA, working on the topic that you will hear her speak today. But a little bit of where she comes from. She did her undergraduate all the way to a master's, in fact, an integrated master's between physics and astronomy at University of Edinburgh. And her advisor is somebody that many of us know very well, Ken Rice. And she, of course, worked on exoplanets and particularly how the star's evolution affects exoplanet systems. And then she moved to London at UCL, University College London, where she worked in the ExoMol group with somebody who also many of us here at CFA know, Tennyson, especially people who do spectroscopy and interested in atoms and molecules. And there she did her thesis on modeling phosphine spectra. Yes, the same phosphine that you've heard recently about. Clara has been working on it for the last many, many years. And in fact, she is I venture to say, the world expert on phosphine. More exciting, though, is Clara has used all this time to develop approaches, both theoretical as well as numerically theoretical, to allow for large, massive calculations of molecular spectra, which has and remains to be a big problem for us users who want to use it both for spectroscopy of exoplanets' atmospheres, but more broadly, I would venture to say also cool stars, and even more broadly, understanding not just the atmospheres, but the spectroscopy of molecules, even in laboratory experiments. So this has put her in the forefront of many exciting projects, and you've certainly more recently have heard about the work on Venus's atmosphere and phosphine there. But I want to point out that it is a very broad work of what Clara is doing, and it's more quantum chemistry and physics than simply application to atmospheres of planets or exoplanets. And to cap this off, when she was in London, she started mentoring high school students. Many of you who joined early heard some of that discussion, which she then transplanted on this side of the pond. So she's been really doing amazing work with students as here in Cambridge, and I think beyond Cambridge, as far as I can understand from the recent conversation. So it is really a pleasure and great to welcome Clara to CFA. And I really wish that we'll be able to see each other in person soon, rather than on the screen. But now, Clara, you have the screen, and just a reminder, you are welcome to ask questions. I will monitor your raised hands in Zoom, or you can use the chat, and I will try to moderate the question and answer period. So Clara, go ahead.
Thank you for the lovely introduction, Dimitar. So that's all true. I am a quantum astrochemist here at the Harvard-Smithsonian Center for Astrophysics, and I cannot wait to actually step into it. Now, if you attended my ITC talk not long ago, a few weeks ago, then this talk will touch on similar topics, just with a little more depth and breadth. So if you are repeating, I have included a literal music ending to this talk, which I hope will compensate for any repetition you'll endure. Now, all of my work revolves around understanding and simulating the way light interacts with molecules, or molecular spectroscopy. This is, for the most part, as Dimitar mentioned, extremely respectful and fundamental research, but it does have endless applications, some of which are a lot less respectable. And my favorite of those is looking for alien life. So I'll focus on that in this talk. Now, I like to reverse my work and imagine what it would be like to be an alien astronomer on the other side of the galaxy looking for life in our solar system. If these alien astronomers pointed their telescope at our sun, this is exactly what they would see, our sun's spectrum. Now, if they use their universal knowledge of spectroscopy that they would get from their own quantum astrochemists, they would be able to learn exactly which molecules and atoms were causing these absorption lines that you see here on the screen and figure out the composition of our sun. And that's because every atom and molecule has a universal and unique spectroscopic fingerprint. These alien astronomers had just slightly better technology than we have now, and they were fortuitously aligned. They would notice that every year, new absorption lines would appear in our sun's spectrum and then disappear, and a year later appear again. And these new absorption lines would be caused by the molecules in our Earth's atmosphere. And they would be able to interpret these absorption lines and learn a lot about us. You can think of our atmosphere and its subsequent spectrum as a planet-sized message, communicating to the galaxy that we have oceans and forests and varied ecosystems with rich life cycles, and also that we pollute a lot. And we can do the same to them. It is fascinating to me that sometime in the near future, questions as ambitious as, does that planet host life, will likely be answered by understanding something as small and fundamental as the quantum behavior of molecules. Of course, that quantum behavior is not trivial. Each molecule has its own spectrum, which look roughly like these, describing how each molecule interacts with light. If we want to detect any molecule on astronomical spectra, we need to know what its individual spectrum looks like. And if we want to interpret astronomical spectra correctly and completely, we ideally want good quality spectrum. To start with, we definitely want accurate spectrum. By accurate, I mean we know the correct location and strength of every relevant spectral feature. For example, in black are my theoretical calculations of the phosphine spectrum that I did with the ExoMol group in London, and mirrored in red are the experimental measurements as provided by the HITRAN database, who have excellent spectra measured with minuscule uncertainties and in agreement with my calculations. So by accurate, I also mean that theory agrees with experiments. But good spectrum is not just accurate. Spectral quality also depends on coverage. For example, this is hydrogen peroxide. In blue, you see all of the current experimental measurements for the molecule. And the features that were measured were very accurate, but that doesn't guarantee coverage in other wavelengths where that molecule is active. And as you can see here in red, theoretical calculations also from ExoMol tell us that hydrogen peroxide actually absorbs in a much wider range of wavelengths than the current experimental data would have you believe. And this isn't a hydrogen peroxide problem. Dozens of molecules have woefully incomplete spectrum. As another example, inverted here in blue, you see all of the experimental measured formaldehyde, which was missing most of its spectrum until recent ExoMol simulations, shown here in red, show that it's spectrally active in many other wavelengths. And in case you're thinking this isn't a concern for the really important molecules, let me tell you about a recent collaboration I did on water. Here in red and blue are two different but widely used assumptions of the spectral behavior of water. And the two agree that water is simply not really spectrally active beyond about 208 nanometers. Almost every atmospheric model that includes water in this wavelength region is currently using one of these two prescriptions. Now, the first thing to note is that these blue lines aren't even measurements, but just a quite reasonable assumption of the water spectrum as it approaches dissociation. The next thing to note is that these don't necessarily show the full picture. In fact, my collaborators and I recently found that well beyond 200 nanometers, water's absorption is weak, but it's not zero. It just never had been measured beyond that point. You can see our measurements in pink and purple, and in black, my most conservative theoretical estimate. These new spectral features of water are way too faint to be used to detect water directly, but that does not mean they are inconsequential. In fact, we found that when these new water spectra were included in photochemical models of planets with abiotic anoxic atmospheres, so roughly analogous to early Earth, Venus, or Mars, the predicted production of OH radicals goes up, and this has drastic consequences for atmospheric composition. Specifically, the predicted abundances of carbon monoxide, oxygen, and in some cases, methane and hydrogen went down by many orders of magnitude. So spectral coverage is really important. But good spectra is not just accurate and comprehensive, but it's also complete. By completeness, I mean, you also know how many features of a given molecule you need to correctly simulate it, because sometimes you need an awful lot. For example, here in white, you see the observational spectrum from a methane-rich brown dwarf. Using an experimental spectrum with 350,000 extremely accurately measured features across this whole frequency range, some of the spectrum could be well replicated. Some, but not all, despite this many features. In fact, in this case, these data could only be replicated with a more complete line list for methane, calculated theoretically with 10 billion features, also by ExaMol. So I've highlighted a few spectral concerns about a few molecules. But as you can imagine, there are many more molecules to worry about. And even with this new improved understanding of these molecule spectra, we're only just beginning to understand what it would mean to actually find them on an exoplanet atmosphere. Take, for example, phosphine. When I first started working on phosphine, it was only known for two things. One, as a marker for violent storms on Jupiter and Saturn. Phosphine is detected in the upper layers of these planets, but it's a little surprising because the temperature and hydrogen pressure there are far too low for the formation of phosphine to be thermodynamically favored. But what happens is phosphine, after being happily formed in the hellish depths of these planets, is then aggressively dragged to the top by strong currents, surviving to much larger concentrations than that predicted by local thermal equilibrium. But on rocky planets like the Earth, we don't have those extreme environments like the depths of Jupiter. So phosphine is rarely made spontaneously. Which brings me to what the second thing phosphine is known for. On Earth, phosphine is mostly notorious for being a lethal and foul-smelling molecule. Phosphine interacts fatally with oxygen metabolism, and that makes it a really effective killer. And for this reason, we often use phosphine as a pesticide, and sadly, also for this reason, we have used it as a chemical weapon for over 100 years in the First World War and more recently by ISIS. So phosphine is overwhelmingly awful and deadly. But what I found is that it has one very important characteristic. For life that doesn't rely on oxygen, phosphine is perfectly harmless. In fact, on Earth, I reviewed all of the reports of phosphine detections, and I found that it's produced in all manners of anoxic ecosystems. Places such as sewage, marshlands, rice fields, lake sediments, the intestinal tract of fish and babies, and actually the guts and excrements of most animals. So I wanted to find out, could oxygen-poor planets have detectable phosphine-rich biospheres? To explore this possibility, myself and my team used multiple detectability metrics and photochemical and radiative transfer codes to figure out whether phosphine could A, survive in a variety of hypothetical oxygen-poor planets, B, be detectable in the near future, and C, be distinguishable from other molecules. My calculations do show that phosphine has a distinctive spectrum seen here in black that sets it apart from other molecules seen here in color. And we found that with JWST, we could detect phosphine on oxygen-poor planets even around active M dwarfs in both transmission and emission with near spec and MIRI respectively, with completely reasonable phosphine production rates. So in brown, you see the production rates we would need, and these are well below those found above the strongest phosphine producing anaerobic systems on Earth, such as sewage plants. Now for sun-like stars, we would find it harder, but still possible to detect phosphine on only a few scenarios, namely the puffy atmospheres of hydrogen-rich planets, and only if their life forms really like producing phosphine. So to detect phosphine on an exoplanet orbiting a sun-like star, we would need something like a full sewage planet or an intestine planet, which I know doesn't sound particularly appealing, but I can assure you we would be disgusting to them too. Still, the takeaway here is that on potentially habitable exoplanets, phosphine can both be detectable and distinguishable from the rest of the atmosphere. And we did these calculations with JWST in mind, so we could focus in the near future. But missions such as Ariel, TPFI, Darwin, Origins, HABEX, LUVOIR, and the 30-meter class of ground telescopes will certainly be able to characterize atmospheres of planets in wavelengths where phosphine is spectrally active. And all this makes phosphine quite promising as a biosignature. But what makes phosphine really appealing is that it seems to have no significant false positives for life as long as it's found on rocky temperate planets. So definitely not a sign of life on Jupiter. To figure this out, we first looked at standard chemical processes, so phosphate reduction and phosphide disproportionation. And unlike the harmothermal production of methane or hydrogen sulfide, we found that in all cases, the formation of phosphine was highly thermodynamically disfavored. So then we thought, what if we inject energy into the system? And for that, we looked to lightning, volcanism, and meteors. And we found that even in the most favorable scenarios, those are highly reduced. Only a negligible fraction of phosphorus could turn into phosphine, and always many, many orders of magnitude below anything we could detect. So at that point, we looked into increasingly more implausible scenarios, and none delivered any substantial false positives for phosphine. So with this finding in mind, I wrote an article with this tweetable conclusion that read, any detectable amounts of phosphine on a rocky planet cannot be explained without life. And when I first submitted this paper, I thought it was a cool conclusion, but it wasn't controversial at all because it was just me describing a totally theoretical, hypothetical situation. I was imagining a distant planet and an anoxic tropical paradise with a rich biosphere producing tremendous amounts of phosphine that we might one day be able to observe, ideally before I retired. You might now know that phosphine turned out to be a little more exciting than I had initially envisaged, because a few months after I submitted this paper, an astronomer at Cardiff, Jane Greaves, reached out to me asking for help with interpreting a JCMT observation, seen here in white, and later a follow-up with ALMA, shown here in orange, that seemed to indicate that phosphine might be present in the clouds of Venus, the only potentially habitable location on that planet. Now, Jane knew this was strange, but needed a phosphine expert to know how strange, and that's how our collaboration began. Because so little is known about phosphine, I also had to estimate the spectroscopic properties of the presumed phosphine transition. And these did seem to correspond to a phosphine concentration of parts per billion, which is much higher than the parts per trillion or quadrillion that we find on Earth. So at this point, we expanded the analysis we did for my earlier paper on the possible formation pathways for phosphine on hypothetical oxygen-poor planets and applied it to the very concrete example of Venus. And we couldn't, no matter how hard we try, explain such amounts of phosphine on the clouds of Venus with any conventional physics or chemistry. So the notion that phosphine, a molecule I had claimed to be a promising biosignature, might be present on Venus is, of course, very exciting. And the press thought so too. But before we jump on life as an explanation, I should point out that there's still much about Venus we don't understand. So all we really know is that something strange is happening. Currently, there's plenty of controversy surrounding this potential discovery, and I'm happy to discuss that here to some extent. But ultimately, what we need to do now is address the primary uncertainties of this discovery. Namely, is the signal definitely real? If it is it unambiguously phosphine? And if it is, what's making it? To try to answer these questions, I am trying to get more data by looking at Venus in the infrared later this year. And as we learn more about Venus, perhaps we can get better models that can help us make sense of exactly what's going on there. But to make the most of both models and observations, we need better spectroscopic data that can not just describe phosphine, but every other atmospheric component of Venus and how they interact with one another. This spectroscopic toolkit is vital for us to understand what is happening on Venus, and I am working on it, namely with a student-led collaboration at the University of New South Wales. But what I want to highlight at this point is how a virtually unknown and quite unusual and quite awful molecule became such an important piece of puzzle in the search for life beyond Earth. And phosphine is just one molecule, Venus just one planet. Even if it does turn out that indeed we have found phosphine on Venus, this will not be the last time we find a potential biosignature on a planet beyond ours. So the question is, will we be better prepared to interpret such a discovery next time? Well, that's where I spend most of my time working towards. Take, for example, these slightly more popular and palatable biosignatures. These are molecules that life we find pleasant loves, such as methane and carbon dioxide, which are produced in large quantities by life, but also molecules like hydrogen cyanide, which aren't particularly popular now, but popular biosignatures now, but it was likely crucial as a building block of life. So it's a good pre-biosignature. We know of these gases, and we can and should look for them in exoplanet atmospheres. But none of these molecules on their own would necessarily indicate life because they all have false positives. And this is true for most of the atmospheric gases that life loves, but it isn't a cruel astrobiological coincidence. This false positive problem happens because the chemical potential energy gradients that life likes to exploit are also easily exploited by geochemical processes. Basically, these molecules are great, but thermodynamically speaking, they're easy to make. And so detection of these molecules in isolation on an atmosphere would not necessarily indicate life. The main solution to this false positive problem is to just carefully consider context. Oxygen on its own may not be a good biosignature. If our sun had different levels of radiation at critical wavelengths, or if our oceans were evaporating from a runaway greenhouse effect, or if we had more CO2 and less volcanic emissions, or simply if the trace gases in our atmosphere were different, then large amounts of abiotic oxygen could accumulate in our atmosphere, and then oxygen would be a false positive for life. But in the exact context of our planet, our sun, and the other components of our atmosphere, oxygen is a wonderful biosignature. And the same is true for most abundant gases usually considered in the search for life. These molecules are only good biosignatures if they can be attributed to life after an investigation of the false positive scenarios, which requires not just an understanding of the stellar and planetary environment, but crucially, the detection of other potentially much less abundant atmospheric gases that can provide chemical context to these discoveries. And how many molecules could form this context? Well, my old group at MIT tried to come up with exactly this list of all the possible gases that could form the context of an atmosphere. And that list contains 16,367 molecules. Now, most of these molecules will likely be present in only small quantities in any atmosphere they find themselves. But their presence would give us vital clues to interpret their environment and any potential life within it. So at the very least, we should be able to detect them. But for that, we need their spectra. And sadly, out of those thousands of molecules, we only have a rough idea of what 600 or so of them look like. And we only have good spectra for a few dozen of them. That means we only have spectra of any quality for less than 4% of possible biosignatures. For all the other molecules, we have no spectral data at all, which means no hope of remotely detecting them. You may wonder why that is. We could record these spectra in the lab, but these experiments are expensive, often dangerous, and sometimes altogether impossible, and would also be restricted by the instrumental limitations of these measurements, as you saw earlier with hydrogen peroxide and formaldehyde. The alternative is to simulate these spectra, which is what I did for my PhD, but that is also not trivial. I won't go into the details of that here, but the general overview is that to get a molecule spectrum, what I do is I study the unique structure and electron distribution of a molecule and use that to solve the Schrodinger equation. First, for the motion of the electrons, and they'll give me a potential energy surface on which to solve for the motion of the nuclei, which in turn provides me with a list of energy levels that a molecule can occupy. But I also map the distribution and motion of the electrons, which is unique for each molecule. And this is called the dipole moment surface. Then I bring these two sets of calculations together to get transition moments, which tell me how likely transitions are to occur between pairs of energy levels. These provide Einstein coefficients, which can be transformed into intensities. So now with frequencies and strengths, I can simulate the full spectrum for this molecule. But these calculations are really hard. Part of the issue is that for each type of molecular excitation, and there are usually millions of them, solving the Schrodinger equation relies on diagonalizing enormous matrices. And this is a process that to the largest extent cannot be parallelized or interrupted. So to theoretically obtain spectra, it takes years of work per molecule and enormous computing power. Even a small molecule with something like 3 or 4 atoms will take at least a couple of million CPU hours, and we usually have to assign each molecule to a graduate student to focus on for the entire duration of their PhD. Take phosphine. We know it pretty well because I spent a large chunk of my 20s simulating its spectra and associated properties. And I would love to repeat what I did for phosphine to obtain spectra for those thousands of biosignatures without spectra, but I'm just one person. And to do phosphine, a single molecule, took a lot of tears and sweat and computer effort and 4 years of my life, which means if I was going to tackle those remaining thousands of molecules at the same rate, I calculate it will take me over 60,000 years, which is too long. And I came to this realization a few years ago when I was writing my PhD. At the time, I was also the head of education for the Twinkle Space Mission. Twinkle Space Mission is planned as a teeny UK satellite for the characterization of planets. And at the time, I was delivering all of the education and outreach programs for the mission, but I was doing this while I was also training as a high school teacher in a North London school, which, by the way, was a terrible decision because it turns out teaching middle school science is way harder than astrophysics or quantum chemistry. But while I was trying to teach as best as I could, I noticed that whenever my research was mentioned in the classroom, the students and I would get into really interesting discussions, which made me think, what if I wasn't working on these thousands of molecules alone? So I created a new program called Orbits, or Original Research by Young Twinkle Students, and recruited 15 of my own kids to research molecules with me and 3 junior scientists who agreed to help. And this is the first cohort of students, which I split into 3 groups, each dedicated to studying the spectra of a molecule crucial for understanding exoplanets and their host stars. So I'd like to introduce to you Team Titanium Oxide, Team Acetylene, and Team Methane. These amazing kids learned astrophysics, quantum chemistry, programming, scientific writing, and performed original research on these 3 molecules. They went from being my high school students to my scientific collaborators, and now are co-authors on multiple papers with their schools as official science institutions. These students you see here then became mentors for next year's students and those the year after, and so on. I hired someone to replace me when I left the UK to move here. So the program continues without me, and since 2018, more than 100 school kids have become published authors of scientific papers through the Orbits program. We found that students who participate in Orbits are also more likely to take advanced STEM classes when given the choice. So still small number statistics, but it does seem very encouraging. To continue this sort of work in the US, I became the director of the Harvard-MIT Science Research Mentoring Program. In it, myself and a small admin team recruit 3 to 8 junior scientists, so mostly postdocs and senior PhD students, and help them adapt their current astrophysics project to benefit from student collaborations. I then train and pay a salary to 10 to 15 local high school students and assign them to mentors with whom they perform original research throughout the academic year. At the end of the program, we organize a scientific symposium for the students to present their research to the community, and I hope you'll all attend this year. In fact, I'll take a sip of water while you add this to your calendars, but I'll also post a link in the chat. And our applications for next year's cohort will open in a couple of weeks. So if you know any high schoolers in the greater Boston area who would be interested in joining the program, do send them our way. Finally, I also run another program, JURA, or Junior Research Award, which is aimed at high school and undergraduate students that have extraordinary potential, but don't quite fit into these other programs. For example, Emmeline is working on cataloging planetary disks. I'm currently supervising Asma and Kara to further improve my phosphine spectrum, and we are almost ready to submit. And Megan and I are working on a full investigation of the detectability of potential pre-biosignature gases, such as hydrogen cyanide. So it isn't just me anymore. By training and supporting students, we are able to work on obtaining their molecular fingerprint for several new molecules, putting a small dent in the list of thousands of potential biosignatures that still need spectra. In the meantime, I calculated that if everyone I have trained joins the effort to obtain all these spectra, and the kids may very well have other career plans, but if they didn't, if they joined us, we could reduce those 60,000 years to a much more reasonable 2 decades, which is really encouraging. It just isn't enough. For example, JWST will start providing astronomical data in a couple of years, fingers crossed. And ideally, by then, all of this fundamental spectra should be ready and tested and integrated into atmospheric models. Otherwise, JWST will provide us with incredible data, but from which our insights will be necessarily limited. We need these data quickly, but currently measuring or simulating all the necessary spectra on time is an impossible problem, which is why I created RASCAL, or Rapid Approximate Spectral Calculations for All, to simulate approximate spectra for those thousands of molecules using a crafty combination of computational organic chemistry and quantum chemistry. The first iteration of RASCAL works by identifying which groups of atoms and bonds, known as functional groups, form spectrally active features within a molecule. For example, every ketone with these atoms will have a feature around here, and every alkyne within a triple bond of carbon will exhibit a feature in this region. And the same applies to literally hundreds of functional groups, which my team and I have now spent years collecting and assessing and coding into RASCAL. We wrote a Python code using chemoinformatics modules to identify every spectrally active functional group within a molecule. And then I use that information to basically puzzle together a molecule's skeleton spectrum, which looks more or less like this. Here is RASCAL spectra for dimethyl sulfide, which on Earth is a volatile produced in reasonably large quantities by algae, so a powerful biosignature. RASCAL starts by recognizing that in this dimethyl, the central sulfur atom does little for this molecule spectrum, and it's the hydrogen and carbon functional groups that do most of the spectral work. With this information, it predicts the approximate position and relative intensities of this molecule spectral features, and it does so correctly, as we can see by comparison to the PNNL spectrum. Though I note, I do overestimate the relative strength of the feature at about 1,000 wave numbers. But what about a more complex molecule, like you see here for ethane diamine molecule? For this molecule, RASCAL identifies the 5 functional groups you see on this table and predicts one strong double feature here with a set of medium complex features here and a really weak feature here. And it does so correctly, as seen by comparison with NIST. And these are just 2 examples, but RASCAL correctly predicts a comparable skeleton spectra for any molecule I've thrown at it. Here's one final example of RASCAL spectra. This is glyceraldehyde. It's present in protoplanetary disks, but it is also the simplest sugar crucial for energy metabolism of all life on Earth. So a really interesting molecule. And I would love to show you how well RASCAL does in simulating this molecule, but there's no infrared spectrum to compare it to, despite glyceraldehyde being an extremely important molecule. But I can at least obtain approximate spectral data for glyceraldehyde and for thousands of other molecules. And it only takes me a couple of seconds per molecule. So it may not yet be the most accurate spectrum yet, but it is extremely quick. If you were to compare it to my phosphine spectrum, you'd be looking at a process that's about 63 million times faster. So RASCAL does this by predicting the main spectral features of over 16,000 molecules, which is more molecules than any other public database in existence. So for hundreds of molecules for which there is experimental data for comparison, and by extension, for thousands of molecules for which there is no other data, RASCAL can correctly approximate infrared spectra. And this is just the preliminary version of RASCAL. Even at this early stage, it is useful. I won't go into the details of all the possible applications for RASCAL, but beyond producing approximate spectra, there's a lot of cool things that one can do with this big data approach to molecular spectra. For example, RASCAL can find spectral patterns within molecular groups by filtering by structural properties. And this is particularly important because it helps us figure out which molecules should be prioritized for the more costly computational or the more dangerous experimental ways of getting spectrum. But RASCAL can also filter molecules by spectral properties, which means I can tell you which molecules are promising absorbers in any given atmospheric window, and also which molecules would be good candidates to explain particular atmospheric features in your data. But perhaps most importantly, RASCAL can tell you which molecular detections are vulnerable to misassignments and degeneracies. I'll give you an example. Take hydrogen cyanide, one of the pre-biosignatures I mentioned earlier. Its infrared spectrum can be completely explained by this one functional group. Through its bending motions and its stretching motion, it forms the 3 main features of the HCN infrared spectrum, which means if you're seeing these features, you may very well have detected HCN. However, every other molecule with this functional group will have similar features. For example, acetylene has the same functional within it, twice actually. And as such, acetylene and HCN have extremely similar spectra and are really hard to tell apart. And sadly, this isn't just an issue of distinguishing between acetylene and hydrogen cyanide. RASCAL can tell you that no less than 890 molecules have the same functional, and as such will have similar features. So distinguishing between these molecules will require either much higher resolution or the consideration of other functional groups within the molecules. For example, the most spectrally active functional group for propene and 1-butene is just the same as HCN and acetylene. But RASCAL can tell you they also have additional spectrally active functional groups, which you can see here in green. So it's really important to note that very often a molecule's strongest feature is not that molecule's most distinguishing feature. And any molecular detection that does not take into that consideration will be vulnerable to false positives, false negatives, and misassignments. So RASCAL is great because not only does it produce approximate spectra for any arbitrary molecule, it has all sorts of useful applications that are only possible with a really large database. And RASCAL 1 can do all this cool stuff, but I am already developing RASCAL 2, which will have many improvements. If I can get a permanent job in the next year and a half before my fellowship ends, then I expect that this work will be completed within the next 5 years. So do keep me in mind if you know of any department looking to hire a quantum astrochemist who's really good at getting science out of kids. So with RASCAL 2, which I will summarize in a minute, I am first expanding from the infrared into the optical, the UV, and the submillimeter wavelengths where it's possible. But I'm also estimating band shapes by using quantum chemistry approximations to add flesh to that skeleton spectra that RASCAL creates. And this will make them able to be used as cross-sections for input in atmospheric models. I'm also expanding from the gas phase into liquid and solid spectra so that I can, for example, help characterize ices on Pluto and icy moons. And this is actually work that I began many years ago when I was a master's student. And finally, I'm harvesting absolute intensities from lab data where it exists and from standard and machine learning quantum simulations such as these where I can do them quickly. Now, of course, for the molecules we care about the most and need very high resolution spectra, we should be able to use high cost computational chemistry to obtain molecular spectra like I did for phosphine. We just won't be able to do this for all molecules, not anywhere near, which is why RASCAL is so important. Given how difficult it is to obtain high quality data for all those thousands of potential atmospheric gases we might want to detect, it is crucial that we invest in intermediate approximate steps to obtaining spectra that can be gradually improved upon, so that one day we can do more than just tentatively detect a promising biosignature. And this isn't trivial to even understand a single biosignature. For phosphine, I first studied why phosphine is avoided by most life on Earth and what kind of biochemistry would like it, and that's anoxic biochemistry. We then looked at the thermodynamics of phosphine production to figure out what its potential false positives for life are, and we found there was very few. But only then did I, together with my team, combine this thermodynamic and biological assessment of phosphine with a consideration of its atmospheric and spectroscopic potential as a biosignature on alien worlds, and found that indeed it's a pretty good biosignature. So critically assessing the biosignature potential of a single molecule is a lot of work. But such an analysis can and should be made for all potential biosignature gases so we can rank them and study them in the context of every possible planetary atmosphere that we will observe in the coming years. Currently, a graduate student in my old group at MIT, Zuchang Zhan, is using my work on phosphine as a template to investigate isoprene, which turns out to be an interesting, but sadly not very good biosignature. But such a thorough analysis could be made for hundreds of other molecules, such as some members of the halocarbon and hydrocarbon families, which may turn out to be valuable biosignature gases with low false positives, but have never been properly studied. As much as I like phosphine, and I do, and as much as I like the more traditional biosignatures like molecular oxygen, which I do, I don't expect that the detection of life will come from a single molecule. As the Venus story shows, the detection of life will likely be uncertain. And that uncertainty will only be reduced if we are willing and able to both detect and understand more molecules, even if they're not pleasant or abundant. Because just because a molecule isn't abundant does not mean it's not significant. It may be harder to detect a trace gas that has a small impact on its atmosphere spectrum, but if we want to reduce our chances of false positives and consequently increase our chances of actually confirming life, we have to be willing to consider the big picture. Not just a few promising molecules, but all possible molecules that can together help us reduce the ambiguity in the detection of life. In summary, to detect life, we'll definitely need bigger and better telescopes. And within the next few decades, we'll be able to point these bigger telescopes at a potentially habitable planet. And we'll be able to look at its spectra, but these spectra could contain many molecules beyond those that we are familiar with. And today, we are not quite prepared to both detect and understand the presence of most molecules on an exoplanet. So my biggest professional concern is not that we will fail to detect a habitable planet in our lifetime. My biggest professional concern is that we will point our telescopes directly at an inhabited planet and just not have the tools to know it. With methods like RASCAL, I want to be ready to detect every molecule that provide insight to what is happening within every observable exoplanet. But this work is nothing without contributions from a lot of wonderful collaborators and students. Ultimately, it will not be the next generation of telescopes that will revolutionize astrophysics, but the next generation of scientists. And in the coming years, I want to do all that I can to help them. But looking for life is very much an interdisciplinary science. We need astrophysicists and engineers and biochemists and quantum chemists. But when the time comes, we will also need philosophers and poets if we are ever going to make sense of it all. So the last thing I want to show you is what happens when you add musicians to this list. This deceptively simple phosphine spectrum is actually formed from the collective force of 16.8 billion tiny spectral features, all of which I've painstakingly calculated. And each of these individual features represents a very particular form of quantum vibration and rotation of the phosphine molecule at very specific frequencies of light. With this spectrum, phosphine can now be detected anywhere in the galaxy. But the underlying complexity of these vibrations, these frequencies, is hard to visualize and even harder to understand. The vibrations at particular intensities and frequencies is just what music is. So I recently collaborated with the composer David Ibbett, who was able to map the spectral behavior of phosphine to the audible range, effectively sonifying phosphine. So this is what phosphine looks like, but this is what phosphine sounds like, transformed into a solo cello piece that captures the complex raw vibrations of its quantum behavior. Recently, I was lucky to hear Minjin Chung perform this piece. So now I will invite you to sit back and relax into the end of this colloquium and spend the next 5.5 minutes listening to the wonderful sound of the terrifying and mysterious phosphine molecule. Form of quantum. So I hope you enjoy the sound of phosphine as much as I did by collaborating with people of all ages and fields, and by using state-of-the-art computational chemistry to consider all possible atmospheric models. I aim to provide the tools to understand alien biospheres so that one day we'll know life when we see it. Thank you.
That's amazing. Thank you, Clara. Wonderful talk, and what a way to end it. Great piece. Well, it's time for questions, and I see that people already raising their hands. Erwin was first. Erwin.
Well, I had two questions. The first one was about the end. I was just curious how you decided on a cello as the instrument of choice, as opposed, say, to a quartet or even a whole orchestra. You had enough materials, so to say. I was wondering why you chose the cello, or David chose the cello.
So David chose the cello. I just guided him through kind of the different movements are different main spectral features, each with their own internal row vibrational structure. And that's what he was trying to capture and why it sounds so harmonious. But he is also trying to see if it sounds more appropriate in an orchestral arrangement where different forms of vibration are performed by different instruments. So he's working on that right now, but he's saying it's really hard. And when I tried to ask him, why is it so hard? He gave me all sorts of kind of jazz lingo that I did not understand. So sadly, I won't be able to communicate it all, but I cannot take any credit for that amazing piece. I just was a scientific consultant.
Anyway, amazing. The scientific question, sort of, that I wanted to ask about was all the molecules that exist, and you have this approach, this RASCAL approach. Are there any other kinds of approach that might be more appropriate for many molecules? You devoting any time to thinking of that kind of entry into this area?
So RASCAL, as far as I can tell, is the fastest one to do large-scale molecules because it's quite simple in a way. But for molecules that we need better resolution or that we just need cross-sections now, there are lots of approaches, and there's been some real advancements in using machine learning in quantum chemistry. And I am using those to produce intensities that I can overlay on RASCAL. So as with a lot of spectroscopic work, it's about collaborating between experiments and theory, and RASCAL is no different. And so RASCAL works surprisingly well, but it benefits immensely from these alternative methods, which I'm always working on.
Finally, let me say that was a phenomenal talk. I enjoyed it immensely.
Thank you, Oren. I want to find out if it was the first time a classical piece has been played in a CFA colloquium, but
the first time. From my memory, only goes back about 40 years or so, but it's certainly
good enough for me.
It's certainly unique in my experience.
Yes, great. I actually would like to follow up on the question Erwin had, which is when we think about the interaction with the experiments, is there a similar kind of massive adaptable new technique that you would recommend to lab experiments to help push this forward? What I mean is you have a particular requirements or needs to anchor here and there your theoretical calculations or to refine them so that they're useful. Can you see that as a new way in which experimenters can actually help without doing it the old-fashioned way, which, as we know, is very slow and also time-consuming and sometimes impossible? Do you have a similar kind of approach to what the experimenters could do differently, the way you do with RASCAL?
So every single time I meet any empirical spectroscopist, anyone who's measuring spectra directly, I always try to convince them, could I even just give you like 12 molecules that need to be measured in the same temperature and pressure, you know, and they would make such a difference because there's so little data. And I have been told no now innumerable times. And really, I find it quite hard whenever I collaborate with experimentalists to just get it so the setup works for a specific temperature, wavelength range, and single molecule. So even for the same molecule, I have to work with multiple teams across the world to do different temperatures and wavelength ranges. And so there doesn't seem to be much of an appetite to do this sort of large scale, just get molecules in and out, just get some spectra, any spectra. But if anyone here knows anyone who would be willing to give this wild idea a try, I have very much a list of molecules that I would love to measure. For example, one of the things that RASCAL has done is showed me plots of molecules that I know are different. They're structurally different, but we know so little about them that they basically look the same. We don't have enough information to distinguish between the two. But I know which parts of the spectrum to look at in detail to be able to distinguish these two molecules. And so I have my own shopping list of things I would love for experimentalists to do. But between the lack of will and the lack of money, I have not been able to get an experimental counterpart to join me on this trip.
Thank you. Maybe we can talk offline sometimes about this. I'd love to talk to you. Next question from Randall.
Thanks very much for a wonderful talk. As I'm sure you're aware, there's now a lot of interest in the journals, at least, and throughout, in getting error estimates on calculations, even though, as we all know, it's nearly impossible to get truly reliable ones. Is there any way within RASCAL to estimate or even approximate what the uncertainty might be in your results, or to find out which results are more likely to be reasonably accurate and which ones are more extrapolations?
That's an excellent question. And I wish I had a slide for that. You're right, it is extremely hard to estimate uncertainties from theory because usually they're done by just comparing to reliable experiments. Now, in the case of RASCAL, the whole point is that there aren't many reliable experiments to do this. So what I've started doing, and though this is very much a work in progress, is figuring out fundamental structural rules that determine these uncertainties. So although every functional group, independently of what molecule it's in, behaves more or less the same, it deviates depending on the rest of the molecular context that it's in. And it seems to be that some proximities, for example, to additional functional groups shift the target functional group more than others. And so I'm trying to make all these rules embedded into RASCAL so I can say things like, here's a spectrum, it's my best guess, but I know that this feature is more likely to be uncertain than this feature. And so I can start quantifying these uncertainties and having at least uncertainties on my uncertainties in this infinite uncertainty loop. But yes, there are rules, and I've already found a few rules. Things like atoms that effectively anchor the functional group they're adjacent to, and depending on how heavy that atom is, I can predict the size of the shift. And so some of this work has already begun. And I've also started predicting uncertainties in the opacities themselves, where I can tell you the spectra isn't quite right, but I can tell you approximately the percentage of opacity you're missing within a wavelength bin. So again, not perfect, but it's a start on assessing exactly these uncertainties that, as you mentioned, are really difficult to quantify.
Thank you.
Great. Next, Martin.
Hi there, that was absolutely terrific. It was even better than the ITC talk you gave, so bravo. But so I wondered, you've said it took a couple of seconds to do each molecule in RASCAL, and there were 16,000, so you must have finished them all by now.
I have, yes.
And so from that, can you identify subsets of more promising molecules that are more likely to provide unique biosignatures?
So that
usefully small set.
So excellent question. And the answer basically depends on the target atmosphere. So I started by doing things like, if it's a methane-rich atmosphere, what are the wavelength windows where methane is not being a strong absorber? And so molecules are weak and not particularly abundant, could be detected within those windows. And then I say, well, if you find a feature in this window, it could be one of these 412 molecules, so narrowed it down a lot. And if you have access to this other window in the same methane-rich atmosphere, and you find features in both, it can actually only be 27 molecules. And so I have RASCAL doing this narrowing down of potential candidates. And then the idea is that I get someone who knows more about photochemistry and atmospheric chemistry than me to look through those 12 and say, well, 8 of those wouldn't even be volatile amongst these radicals, so we can get rid of those. And my goal is to primarily, with RASCAL 1, highlight the uncertainty and the ambiguity in these potential detections. But sadly, I can only highlight the problem. I can't yet solve it, but I can start building these potential candidate lists, which will be, I think, the next step for us to be able to actually determine which molecules we're looking at.
Great. Andy, you're next.
Oh, hi, Claire. That was a brilliant talk, by the way. Boy, I really enjoyed it. You know, there's been a lot of stir in the press recently that you know, we should get on top of methane as a greenhouse gas than on Earth. And there's been a tendency to sort of push methane to the side because it's not particularly durable, has a short lifetime. I wondered, I realize it depends on the photochemistry and the radiative transfer in the particular planet's atmosphere, but do you have a feel what the lifetime of a phosphine molecule is, for instance, on Venus? You know, does it accumulate, or would there have to be a continuous resupply?
So that depends on the type of atmosphere. So on Earth, the lifetime of phosphine is about 28 hours based on the radicals that we have. But on Venus, because the atmospheric composition and the radicals and the photolysis vulnerability changes so much as the thick atmosphere goes down, that it varies immensely. So phosphine's lifetime on the top of the clouds is seconds. It disappears almost immediately. And then within the clouds, we get longer lifetimes, all the way to months and even years at the very bottom of the atmosphere. And so depending on where you're finding phosphine, it becomes more or less of a mystery, though it is weird no matter what, based on the altitude you find it in.
Well, the paper that you pointed me to, that was sort of like it's the worst case, right? Because it's in the middle, right? It's sort of mid-atmosphere. Do you have any feeling for what the persistence time would be there?
So it's approximately hours, hours to days, depending on where exactly in the clouds. We still have enormous uncertainties with the actual altitude we're probing with our multiple observations of Venus. So this just paints a picture with quite how little we know about the Venusian clouds. If we knew more about its exact composition and the radicals, we would be able to make better measurements and better assumptions. But I should point out that every time we leave the Earth, our estimates of both the radical abundances, but also the reactivity of these radicals with the molecules we care about, becomes really bad. Most of the reaction rates that we have are exactly only for the Earth's atmosphere, which makes sense. That should be a priority, but it means we're really woefully unprepared to make really good, complete photochemical models of exoplanet atmospheres, and Venus is included in that list.
Yes, great. So next, Robert.
Hi, Robert.
Hi, Clara. Yeah, very nice talk. Yeah, so I just had a quick comment, as you probably expect. So obviously, high resolution is one of the, I would say, key points to distinguish between these molecules. And I would say that I don't think we're quite at the stage where ab initio calculations can completely replace experiments. Obviously, we need to validate these measurements. So I just thought it was worth mentioning that, yeah, people are measuring I would say all of these molecules, but they are measuring a lot of the key species at high resolution continuously. And in HYTRAN, as you know, we've added many cross sections actually in the past few years. Hundreds, obviously it's not on the order of tens of thousands, but you know, there's still a good chunk of new data there. So yeah, so basically, you know, people are making these experimental data, and high resolution, I think, is a key aspect here. But regarding the cross sections, have you compared many of these, like hydrocarbons, for example, from HYTRAN or elsewhere with RASCAL?
Sorry, yeah, so the cross sections made by RASCAL currently are pretty rough. And so they look okay position-wise, but their opacity estimates are still very much off. If right now one of us had to stop working, it should be me, because your work is much more important, and getting measurements of high resolution data is absolutely crucial. That will never be something that I think ab initio calculations will substitute. At best, we can hope to complement and to cover the areas that high resolution measurements cannot. With RASCAL, these opacities are very much approximate. With my more higher resolution theoretical work, the opacities become quite good. And specifically, they become better than experiment once you get to high temperatures, because there's just lines that weren't able to be measured. And so it's really at high temperatures that theoretical calculations end up doing really well compared to experiments, because of course they're limited to usually room temperature measurements, and it's almost impossible to measure every single one of the billion transitions. And so experiments and ab initio calculations, now that ab initio calculations are good enough, just become the symbiotic work that I'm hoping will always benefit from one another. But I have no expectation that ab initio calculations will ever supplant experiments where we can get them. Yeah. So thank you for your service.
I had to mention high resolution, sorry.
Yeah, I mentioned HYTRAN. I mentioned HYTRAN. HYTRAN's wonderful.
You did, yeah. As a follow-up then, I just thought I should, maybe I don't know if you've considered this, but so a lot of the exoplanet, well, basically what you end up looking at in the transmission spectra is often the weaker regions between the spectral bands. And as you know, like experiments can't really detect that. And you pointed out with water, for example, that the absorption there is not actually zero, it's just a very small number. Have you tried to fill in the gaps with RASCAL in that regard? So complementing what we already know and just fill in, you know, if there is a suspected band in between, perhaps that's a good way forward to kind of fill in the gaps.
I certainly hope so. Most of these gaps are in the optical and the UV. And so that's very much RASCAL 2. I have barely finished the infrared, and then expanding further, as you know, it's a bit of a nightmare, because then you have to consider things like electronic excitations and approaching dissociation and the weeds, which are all these billions of minuscule transitions that have cumulative opacities rather than individual features. So these are basically a nightmare to simulate theoretically, a nightmare to measure experimentally. And so it's very much a focus of RASCAL 2. But this is work in progress. The water example is a great one in that we should really know water. Everyone agrees water is a very important molecule to know. So how are we in 2021 still making discoveries about the fundamental quantum behavior of water? To me, that seems outrageous, and I'm very pleased to be within that research, but I feel like we as a species should be doing better.
I'll leave it there. Thank you.
Thank you, Robert.
Thank
And
you.
thank you,
Thank you. And that sounds like a wonderful way to wrap this question and answer period. We as a human species should be doing better, Clara, and you did an excellent job. This was a fantastic colloquium, and good luck and all the best in getting RASCAL 2 working and getting us more of this data. We all need it very badly. So
Thank you.
thank
I
you
will try my
again.
best.
Thank you again, and thank you everybody for coming to this. Thank you. Bye.